Okay, our first speaker is Xiangyu Gao. Yeah, please. So Xiangyu is a current postdoc fellow at University of Washington, working with Arvin and Ratu, and he graduated from NYU. His research interest is optimizing code generation and network substrates using like solver-added tools such as programmable synthesis. So here I'll be talking about a system called ParserHawk. How will parser generator using program synthesis? It's your time.
Okay. Thanks for the nice introduction. Hello everyone, I'm Xiangyu. Today I'm going to present our work, ParserHawk, parser-aware hardware-aware parser generator using program synthesis. So this is joint work with people from NYU, Rutgers, Alibaba, and Google. So programmable hardware data plan emerges to support increasing complex network functions. They have been used in several scenarios, such as CDN, edge devices, real-time network monitoring. Programmable hardware data plan spans across a spectrum of devices, such as SmartNICs and programmable switches. A typical network device consists of two main parts, parser and packet processing pipeline. To execute the data plan programs, we need to generate low-level code from high-level abstractions from the developers. Several work have been done to do optimized code generation for packet processing pipelines, but we believe that not much attention has been paid to the parser code generator. This is even more important to do the optimized parser generator at this moment because parser become more complex. If you cannot fit a parser, you can definitely not fit a whole program. So for example, like switch.p4, it has more than 50 headers, hundreds of fields, and more than 100 states. And we can see that we need to develop more complex network packet format, especially because of a lot of cross-domain collaborations, like financial exchanges have their motivation to move their trading platform to the cloud providers. So what is a parser? Basically, parser turns an input bit string with no structure in it into a hierarchy representation of headers, fields within the headers, and bits within this field through a finite state machine. So in this state, parser will compare a lookup header against a key-mask pair to do the transition. For example, here we can define the parsing logic in this finite state machine formula, and this parser turns an input bit string into a map storing the value of field 1 and field 0. So we can consider the parser as a pre-processing step, and it will get some structured value, and then the packet processing pipeline will continue to modify these packet fields. So in this case, suppose the field 0 and field 1 are 4-bit variables. Let's take a look at what this parser look like. It will take as an input 8-bit input bit string, and it will first of all go to the first node, and the first node will assign the first 4-bit to field 0. And then since the first bit of field 0 is 0, it will go to the next state, and then assign the next 4-bit to field 1. So finally, it will go to the accept state by assigning field 0 to 0 and field 1 to 15 in decimal. So if we look at another 8-bit input bit string, the first parser state will assign the first 4-bit into the field 0 as well. However, since the first bit of field 0 is 1, it will go to the reject state, maybe because of this is a malicious packet, but finally we will drop this packet. Okay, so on the other side, we can see that parser architecture, hardware architecture are heterogeneous. Here we introduce two typical ones, single TCAM and pipeline TCAM. So by the way, TCAM is a high-speed specialized memory used in network device for fast search within a table. If we look at this parser program written in this finite state machine, single TCAM fits the whole parser into one TCAM table, where each row representing an entry showing some, hey, what is the state we will extract, what is the key, what is the mask, what is the next state. And then this packet, this architecture can support transition from one entry to another entry, or visiting one entry for multiple times through this self loop. So pipeline TCAM, as its name shows, chains a sequence of pipeline TCAMs. So you can see that all TCAM tables are similar except locating in different places. So we can only support the transition from the table above to the table below. So there, we want to map this parser to single TCAM and pipeline TCAM. So for this particular transition, it will map to the transition logic in single TCAM and pipeline TCAM in this arrow. Similarly, we can see the transition 2 and transition 3 have this transition as well. Okay, so now we can see that on the one side, an increasingly number of complex parser programs are emerging, like switch.p4. On the other side, there are a lot of heterogeneous programmable devices, such as Intel's IPU, NVIDIA's Bluefield, Broadcom's Trident. So each has their unique architecture. So what is really missing is a high-quality parser code generator to bridge the gap between the programmers and the hardware devices. So well, here, hardware high quality means we want to fully utilize the device for the programmers. And we also hopefully want to ensure the retargetability, because this is useful for the cloud providers to generate code across multiple devices to avoid vendor lock-in problems. So unfortunately, existing parser code generators often produce resource-heavy outcomes. So sometimes if you use too many resources, this will lead to a compilation failure because you cannot request more than available resource. Okay, so let's do a little bit math to show like why there could be a bad result for existing code generators. Suppose this is our input parser. It do the state transition based on a 4-bit key, LK HDR, lookup header. Okay, so each row is a state transition row and need to consume one TCAM entry resource. So the goal is to implement the parser using as few rows as possible. To generate the parser node, we first of all need to merge entries using some key mask pairs. So there are two ways to merge it. So the first way need to use 2 entries. The second way only need to use 1 entry. We can see that the second way is preferable. Okay, so afterwards, we forget about the bad way. We are continue from the good way. Okay, so the second way is if we want to do the key splitting, well, we need to fit the state transition key into the hardware constraints. Here, if we need to split the 4-bit key into 2-bit, again, there are multiple options. We can either check the first 2-bit before the second 2-bit, or vice versa. And we can see that the second solution is also better. And in terms of the rows, you can see. Okay, so in addition, we can see that there's even more hardware constraints we have to consider, like extraction key limit, look-ahead window key size, so on and so forth, making the parser generation quite complex. Okay, so we can see that existing code generators incorporate many generation heuristics, but they mostly focus on some local part of the program and are dependent on the developer's programming style. Here, programming style, what I mean is how you write the program using one particular programming language. So this will result to like different programming styles lead to different outcomes, and each outcome might use different resources. So therefore, our proposal is to generate high-quality parser code using program synthesis. At a high level, program synthesis is to automatically generate a code that satisfies the specification. So this will not dependent on the programming style, but only focus on the semantic of the input program. So we developed our system called ParserHawk. This is a general workflow of the ParserHawk. The programmer writes a parser program in high-level language such as P4, and the hardware developer will provide a hardware specification. Then ParserHawk's front end will analyze the input program to output a parser spec and hardware implementation. So parser spec is to develop the parser's behavior, and hardware implementation is to specify the hardware's capability. Then both of them will be fed into a program synthesis engine to output a synthesis output. And then finally, we will do some code generators in the backend to generate output for multiple devices. Here, we generate for Belfort, Tofino, and Intel's IPU. The core part of the ParserHawk is the synthesizer. So let's look at the program synthesis in a little bit more detail. The programmer will write a parser program at using some high-level language. It will specify in each parser node what is the behavior of the parser state. And then the hardware developer will specify the hardware's implementation, the hardware's capability. Mainly ask what is the behavior of each parser state. For example, what is what field you want to extract, what is the transition logic, and what is the transition key. Then we feed them into SIGCOMM'25 counterexample guided inductive synthesis to output a generated parser. So in terms of the first order logic encoding for the implementation, it mainly consists of two parts, the parser functionality and the hardware capability. Parser functionality encodes the parser's behavior. For example, this pseudocode shows that what extraction, what state transition in which parser state. And hardware capability capture both some common behavior and then some unique behavior. So common behavior include like encoding the parser's behavior. Like if you want to extract a field, you may assign the next X bit to this particular field and move forward the extraction pointer by X bit. And then there's also some unique hardware constraints like what is the unique key width limit of a particular hardware. So we use SIGCOMM' loop, and the SIGCOMM' loop is to iterate between the synthesis and the verification phase. So this is some algorithm developed like 20 years ago to speed up the synthesis procedure. So here, the SIGCOMM' loop is to initialize an input set by randomly sampling across the whole input space, and then the synthesis phase will try to find a satisfiable solution that only works for the test case. If there is no solution, meaning, hey, there should be no solution for the whole input space, otherwise, we'll go to the verification phase, and if the verification phase will check the synthesis output is correct or not for the whole input space. If yes, it means we can find a solution. Otherwise, it can find a counterexample and add this counterexample into the test case set and do this synthesis and verification again. So in our ParserHawk, the input space is a bit string contain like I0, I0, I1, I2 until IK. And then we feed them into the synthesis solver to find whether there's a solution or not. If there's no solution, meaning it's a compilation failure. Otherwise, it can output a parser implementations as a candidate to the verification phase. The verification phase will check whether there's some counterexample or not. If there's no, means the solution is our final parser implementation. Otherwise, there's at least one bit string making the verification fail. So we add this input bit string into the test case set and update this input bit string test case and do this synthesis and verification again. However, so naively encoding the parser generation problem as a program synthesis will not work because of the extremely long synthesis time. The main reason is the large search space. So the large search space coming from two parts. The first part is the large search space to define the parser's behavior. For example, if we have one 32-bit variables, it has 2 to the power of 32 possibilities. If we have n such variables, the search space can increasing exponentially pretty large. And second is it comes from the large input space, like the input bit string can be as large as hundreds of bits. So fortunately, there are some redundancies in the search space. That's why we come up with some optimization algorithms. There are 7 optimization algorithms in my paper, and right now I choose one of them called state transition synthesis, which is the most effective one. So state transition synthesis mainly to solve, focus on the speed up process to explore suitable variables, values for the constant variables. So there are multiple parts of the state transition synthesis, including key space pruning, mask selection restrictions, and key space decomposition. I will describe them one by one. So the first one is to reduce the search space of key variables. So this example shows a code generation process for one parser program on the left-hand side and generative one to the right-hand side. We use yellow color to highlight the key variables. So in entry merging steps, ParserHawk want to find some key plus mask combinations to merge multiple entries. So we can find that instead of relying on the synthesis engine to find the values, we can fix them to find constant only appearing in the input program and leaving the flexibility to the parser. So that's why we use this to guide the synthesis solver to find constant values. And this can reduce the search space from 2 to the power of bit width to the number of constants appearing in the specification. Roughly, it's smaller than 100. Okay, the second one is to reduce the search space for mask values. So we need mask to hide certain bits. But if in our specifications, well, there's no two conditions go to the next state, there's no meaning for, it's not meaningful for us to like do this mask selection. So we can safely set most of the mask's value to all be 1 by analyzing the input parser. And this can reduce the search space from 2 to the power of bit width to 1. And third is key space decomposition. They focus on one like very big width constant in the input parser, while the target device constraints are more limited. In this case, if the target device can only fit a 2-bit values, it is impossible for ParserHawk to find a 4-bit variables. So therefore, we include all 1-bit, 2-bit subranges, and this can reduce search space from the exponential to polynomial. To evaluate ParserHawk, we find off some fragments of open source P4 programs and create 58 benchmarks in total, and we rewrite them in semantic preserving ways as well. So we compare ParserHawk against academic compiler and commercial compilers to find like whether some retargetability, some resource usage, and some code generation time. And we can see that ParserHawk can generate code for Tofino and IPU. Remember, Tofino use single TCAM and IPU use pipeline TCAM. So, and also when we switch from one backend to the other backend, it only requires less than 100 lines of code change, which is much easier than writing a code generator from scratch. So in terms of the resource usage, ParserHawk can get 100% successful compilation for all benchmarks, but commercial compilers fail to compile some of them. And ParserHawk also use better resources in terms of its compilation output. So ParserHawk need to finish in 5 minutes for 90% of the benchmarks, which is longer than some baseline compilers, which only complete in 20 seconds. This is one of the drawback of the ParserHawk. But since we have a lot of optimizations, we will show here that the optimizations can offer us around 300 times speed up on average. So we also do some breakdown analysis for like to see what benefits for each optimization algorithms. And then right now we choose state transition synthesis, which I described before, and bit grouping, which is another optimization algorithm, to see that each of them can give us around 10 times speed up. So to conclude, we built ParserHawk, which is a high quality and retargetable parser generator using program synthesis, and the domain-specific algorithms offer a lot of speed up. And in the future, we also want to do parser generations for more parser architectures and parser plus pipeline together. So it is open source. Feel free to have a try. And thanks for listening. I'm happy to take questions.
Very nice talk. Now we have time for questions. Any questions? Oh, okay. I have a question. So as you said in your presentation, right? So it seems that your solution is quite good, but indeed experience a bit more compile time, right? You have quite a few good optimizations, right? Mm-hmm. So you said your solution is compared to baseline solution still slower, right? Yeah. So can you comment a bit on this, whether this slow performance will affect the like, for example, practical adoption of your solution?
So this will not affect the correctness?
No, not practice, adoption. I mean, use it in practice. Whether this brings some like complexities that it's hard to adapt.
Yes, so that's a great question. So this is what we think. So usually network functions are not evolving that fast. So this can afford like compiled once and then use it for a relatively long time. So that's why we think it's okay to afford to spend a little bit more time to find a better solution, but use it like pay once and benefit for a long time. And I think if for the drawback is if you are in the development process where you want to get your feedback quickly, this might be a little bit bad. So that's why this is some of our future work is still working on like continuing improving the compilation time of the ParserHawk.
Okay, yeah. Thank you. Questions? Yeah.
Does the Yeah, does the optimized parser code, does it have any on those specific hardware architectures? Does it specifically improve like latency and packet rate, or does it just improve the capacity of how many parsing rules you can download into the hardware?
You ask the optimization, what is the benefit from optimization?
Exactly. What's the user-facing benefit of the optimization? Is it on those specific hardware architectures? Does it allow? Does the more optimized parser code also provide lower latency or higher packet rate, or is it just a matter of that you're able to because you're using less hardware resources, you're able to deploy more and more parsing rules into the hardware?
Yes. So exactly. So basically, our synthesis is to fully utilize the hardware. For example, like maybe one of the commercial compilers need to use a lot of entries, like 10 entries. We only need to use 2 entries. So this gives room to first off develop more complex parsers to fit more complex parsers. And second is in our like IPU, you can use fewer pipeline stages to reduce the latency. Exactly like what you mentioned.
All right. So let's thank the speaker again.
Thank you.
Yeah.